Okay, good morning everyone. Since we are streaming this right now to the outside world, I am using this mic. Welcome. It is my great pleasure today to have our very own Garrett Cole as our guest speaker. Well, there's so much to say. I think we need several beers about all the stories that brought Garrett to Vienna and then into his many other successful stages of his career. Suffice to say, Garrett got his PhD from UCSB in Santa Barbara in the Bowers group. He was working back then on MEMS tunable vertical cavity surface emitting lasers, which is like as far away from what we are doing as you can imagine. However, but back in the days, we of course started doing this quantum optical control of micromechanics, and I at some point get this email from a postdoc in Lawrence Silvermore National Lab saying, what you're doing is interesting. I think I can do it much better. And so and so Garrett came to Vienna with a Lise Meitner, so with a Marie Curie fellowship, stayed a couple of years, stayed longer, and I still remember, actually he did better, obviously, of course, because what he could do is he was an expert in microfab, and in combination actually with optical structures, so Bragg coatings and so on, which then led to really high-Q micromechanical devices that skyrocketed our performance in quantum controlling. And when we wrote our first paper on that, we were we needed a good story for abstract and intro and conclusion. And then we said, this could actually be interesting to also mitigate noise in these coatings, and we just put it in the conclusion of the paper as sort of a fun story. Lo and behold, we ended up in optical coating meetings at Caltech. I still remember that. We were pitching to the LIGO guys why this could be interesting for them. And I remember some of the really senior LIGO people in the back completely destroying us and saying, and this and this and this are the reasons why it cannot be done. And Garrett, being Garrett, of course, went home, and this and this and this were then the boxes he ticked off to get it done. So basically 2 years later, we had a new technology at hand, and this was the origin story of crystalline mirror solutions. So Garrett left academia, founded Crystal Mirror Solutions as a CEO, CTO, and then later became managing director at the Thorlabs branch of Thorlabs Crystalline Solutions, I think they call it, yes. Until academia called, and now since I think beginning of the year, something like that, he is now professor at the Wyand College of Optical Sciences at University of Arizona, and here to tell us about, I guess, his plans and everything. Yeah. Okay, so Garrett, great that you're here, and Garrett will be here today and Wednesday, so please find time, make time to talk to him. He really knows his stuff. So, Garrett.
All right, thank you, Marcus. Well, that was a fantastic introduction, and it feels like a homecoming coming back. I was here from 2008 to 2014. You'll see today I'll cover a wide range of topics, like Marcus said, something for everybody. So microfab, materials, ultra-stable resonators for making quantum-limited interferometers, and so on. So really, it's been a fun journey on this transition from semiconductor lasers to cavity optomechanics to low noise mirrors. Still have a really nice connection with Oliver Heckel's group here, doing some fun collaborative work that you'll see in detail. And since this is on YouTube, I have to give a shout out to my daughter Fiona, who may be watching. So yay, Fiona, I hope you're on. But yeah, so as you see from the title, the main focus is going to be on these substrate-transferred crystalline coatings. So these ultra-low noise, single crystal mirrors. And this is in direct competition with standard physical vapor deposited mirrors made from ion beam sputtering or evaporation and so on. But I'll also show that this is more of a general enabling technology, like taking the basic manufacturing process that we developed in this direct bonding-based integration approach opens up a number of really interesting application areas. So I'm going to jump in. I'm kind of repeating myself, but I'll give an overview of these crystalline coatings and their advantages. I'll briefly mention how this came to be as a spin-off of fundamental cavity optomechanics work. And then I'll go into more detail on the select applications of these coatings. So the core use case is in precision metrology applications, so making the world's lowest noise laser systems, using these in a reference cavity for stabilizing those lasers. I'll then go on to describe very high performance mid-infrared mirrors, and that's the local connection here with the folks in Oliver's group at the University of Vienna. And there we've made some really pioneering efforts on just the lowest optical loss, highest reflectivity mirrors built in that spectral range to date. And then there'll be just a single slide on showing this, how we can leverage all of this expertise in direct bonding and these semiconductor materials to make a variety of active optoelectronic devices. So yeah, again, just big picture point of view, what's really interesting here is it's a unique intersection of sort of standard semiconductor materials and fab techniques. So you start with, what would be a traditional like wafer scale material. You do standard lithography and etching, but then you can see this turn into ultimately three-dimensional devices. These are no longer standard, photonic integrated circuits or planar light wave circuits. You're using the semiconductor in combination with these bulk super polished optical substrates, or these precision polished optical substrates, to make what I would say immodestly are the world's highest performance precision laser optics. Because now we can integrate these beautiful single crystalline materials into these optical elements. And I think it's an interesting space to work. And the application areas, as I said, core use case are in these optical, like trapped atom, neutral atom lattice clocks, or trapped ion clocks, which are really the absolute forefront of timekeeping in the world. I'll cover this in much more detail in a few minutes and show how our coatings can advance the state of the art there. And the basic premise here is you are scrubbing away all of the excess loss, either optically or elastically, thermomechanically. And at that point, you can make the most stable interferometer. So you can make fully quantum limited optical interferometers where you can see things like quantum radiation pressure noise. You can see back action effects on the end mirrors because you've pulled away these just random wiggling of the cavity end mirrors. And so that's been a long-standing collaboration with some folks related to LIGO. So I'll give some credit to Thomas Corbett now at Louisiana State University and Nurgis Mavalva at MIT for those collaborative efforts. And then in the same vein, working with the folks at LIGO, like Markus said, back in 2008, we were showing, maybe we could take our 50 micron mirrors and scale them up. And I'll show some examples today where we've gotten to really nice macroscopic mirrors. That's a beautiful photo that I keep using from Georg Winkler, who used to be here, on these 8-inch diameter mirrors. And we have a path to get to 12-inch and beyond. And then, as I mentioned, another nice application area are in these mid-infrared cavity-enhanced spectroscopy efforts, which I'll touch on in more detail. So the other fun outcome of all of this, as Markus mentioned, is you can now just go to the Thorlabs catalog and you can put these in your shopping cart and you can buy everything from discrete mirrors, these substrate-transferred crystalline coatings. But the other fun thing was with the additional resources post-acquisition of Thorlabs, we could start making more systems-level, products. So custom or standardized reference cavities, so the fully assembled, optically contacted mirrors and spacers. And we had a really nice partnership with Menlo Systems where we would incorporate these into a vacuum chamber with integrated temperature control and ion pump and so on. And so what's nice here is you can use this as a core element of a cavity stabilized laser system. Again, I'll cover in more detail what that means in the course of the presentation. And most everything we'll do, I'll introduce it here, is in the near infrared. So wavelengths from 1 micron to about 1550. But then we're now going to soon see mid-infrared optics around 3 microns, 3.3, 4.5 microns coming out in the catalog soon, which is quite exciting. So it was neat to see, like Markus said, went from the cavity optomechanics work to the spin-out company to then see that you can commercially buy these. It's been a fun path to see that whole process. And this is a fun little trivia thing. I don't know if it's still true, but as of 1 or 2 years ago, this was the most expensive item on the Thorlabs catalog that shows a price. So most things in the catalog show a price, but some will say, ask for pricing details. And we made the decision to show the price here, which may not have been the best because it's kind of scary. But anyway, it's just a fun little factoid. So now I'm going to go way back to the basics. So I think everybody is likely familiar, but I'm going to walk through just the basics of mirrors and optical coatings just to make sure we're all on the same page. So, there's two classes of thin film reflective optics, and the first we're all going to be familiar with, which would be a gold-coated mirror. And that can be everything from a very low-tech application, like in your bathroom, or side view mirrors on your car, up to like a high-tech application like this segment of the James Webb Space Telescope, right, which is gold-coated, super polished silicon carbide. You know, the challenges with those mirrors are you can get fairly modest reflectivity. You know, take a single layer of silver, aluminum, or gold. It may or may not have a dielectric protective layer. And you'll get something like 96, maybe 98%. But keep in mind that anything not reflected is going to be absorbed in that optic. You're not going to make a transmissive optic. It's going to have low damage threshold, again, because of this significant absorption and so on. And so to get beyond that, if you have an application that requires much higher optical performance, you're going to move on to what's known as an optical interference coating. And the basic premise is that the constituent materials that make up this mirror are transparent. It's no longer inherently absorbing like a metal, so you're going to choose something like a silica-based coating or a tantalum pentoxide or some other metal oxide most commonly. And if you properly design these structures and have a good process technology, you can get to extremely high reflectivities here, approaching unity reflectance. The difference, though, is you cannot do this with a single layer anymore, right? If you look at a piece of glass, like the glass window there, you get 4% reflectance off that surface. But what you can do is you can build up, in this case, a distributed Bragg reflector, which the simplest design is alternating high and low refractive index materials, each with a quarter wavelength and optical thickness. And what you rely on here is that you have all these little Fresnel reflections at each of those interfaces, and these add together constructively to give you a narrow band region of high reflectivity, and I'll jump back in a second. So it's not going to be broadband like the metallic mirrors, but you're going to have a narrow band region of quite high reflectivity here. And one thing to point out, because this will be important later, is that you have a fairly rapid drop-off in the optical field intensity as you go into that mirror. Again, because you're, all the constructive interference of these little individual reflections inside. So the point here, again, you have this short interaction length, and you ultimately have three loss mechanisms in those mirrors. So the first is a design parameter, and that's how much light do you want to transmit through that structure. And that's going to be controlled by the refractive index difference between the layers and then how many layer pairs you stack up. And then you have two other unwanted or excess loss components, which are absorption and scatter. They're, I think, quite obvious by their name. You have photon absorption due to like defect states or impurities or above band gap illumination or even nonlinear multiphoton processes. And then you have optical scatter due to just surface imperfections or defects or interfacial roughness and so on and so on. In a well-developed technology, you can maintain total sum of those losses at the part per million level, which is incredible to think about, right? Throw 1 million photons at that surface and you're going to get one to a few lost, right? You can basically get all of those back. And ideally, you want this absorption and scatter to be less than the transmission of the optic, because again, you want to be transmission dominated in that mirror. So the current state of the art to make such mirrors is known as the ion beam sputtering process. So especially in the visible and near infrared spectral range, this will be the sort of process that you would choose as the gold standard for making ultra-low-loss multi-layer mirrors. And this was developed initially for ring laser gyroscope applications in the mid-1970s. That was the first application that needed extremely low loss to function. And these are most commonly transition metal oxides. So tantalum pentoxide is the high index material with a refractive index around 2, and then silicon dioxide is the low index with a refractive index around 1.4. And it's a really nice scalable process. You take an ionized beam of noble gas atoms, you put them, impinge them on a source target, which can either be a direct oxide or a metallic target in an oxidizing environment, and you're effectively going to spray coat this material onto a carrier substrate. And imagine you have a big chamber, you could put a bunch of these substrates around, you could simultaneously deposit on these substrates. You have very good process control by modulating that ion beam, by swapping targets and so on. And again, there's a lot of, this is a very mature technology. Developed in the mid-70s, you have 50 years of development behind it. And there are some limitations, of course, as with everything, it can't be perfect. So one that we're going to talk about today, which is very niche, but something that is of interest to the community here, which is excess elastic loss, which controls the thermomechanical loss in the system. Also, these have very poor thermal conductivity. These are glassy oxides, maybe 1 watt per meter Kelvin thermal conductivity, and they have strong mid-infrared absorption. So again, they work very well in the visible and near infrared, but when you get to wavelengths beyond 2.5 microns, you start to have excess absorption in these systems. Interestingly, just coincidentally, the same time these ion beam sputtered coatings were being developed, you had the first demonstration of an all-epitaxial, so a single crystal interference coating that was demonstrated by Bell Labs circa 1975. And at that time, it was just a scientific demonstration, just a curiosity. We're going to make a gallium arsenide, aluminum arsenide multilayer, and look, we can make an interference coating out of this. This has really come into large-scale commercial use with the advent of vertical cavity surface emitting lasers. Like Markus mentioned, that's the background I came from for my PhD. For those who are not familiar, it's a really interesting class of microcavity laser diodes where the light emits normal to the plane of the wafer. Normally, with these semiconductor lasers, you have a waveguide and you have a long in-plane structure. But here you have two high reflectivity Bragg mirrors, that same interference coating I just showed. The light resonates between those and then is emitted normal to the surface of the wafer. And these have huge commercial use cases now. Optical mice use them, discrete applications use them, short-reach datacom applications use them. Every smartphone with a facial recognition system uses an array of these to generate the point cloud on your face and so on. So, I mean, billions of these lasers are made per year. And so, and one of the integral components of these are these integrated Bragg mirrors, right? And so these are produced in mass quantities, but you can't go to your favorite coating shop and be like, give me a AlGaAs mirror. That just does not happen. And the reason being is this last bullet point here, which is lattice matching constraints. This is grown in a single crystal growth process, right? So that heavily restricts which substrates you can choose. So you're going to have to use a crystalline template with the same interatomic spacing and the same symmetry as what you're trying to grow on top of it. So you're basically stuck with planar gallium arsenide. So again, great for optoelectronics and these sort of micro-scale photonic devices, but not for general coating applications. But of course, sometimes there's drivers or things that force you to sort of think differently and come up with a solution. So as Markus alluded to, back in the olden days, in the early days of cavity optomechanics, I don't have time to do this field justice. I think many in the audience will appreciate this, but my quick optomechanics discussion is you're going to leverage the same tool set that you would use from AMO physics to cool trapped atoms and trapped ions, but you're going to cool select mechanical modes of a mechanical resonator. Back in the day, we would take some simple cantilevers or other basically micromechanical devices, and we would use this as one mirror in an optical cavity. And then you would use radiation pressure effects, intracavity, properly detune that cavity, and you could cool those select mechanical modes of that device. And the mechanical requirements here are the physical requirements are you wanted very high reflectivity, you wanted to make a relatively high finesse cavity, you wanted low optical loss because you didn't want photothermal effects and so on. And then you needed a high mechanical quality factor. You wanted this device to have a really narrow mechanical resonance because that acted as a filter. The surrounding thermal bath is trying to pump phonons back into that system. And with this nice narrow mechanical resonance, you could reduce the rate at which that sort of heating process happened. If you flip that mechanical Q, you get what's known as the elastic loss angle, which is the intrinsic sort of phonon loss in the system, the imaginary component of the Young's modulus of these materials. So, circa 2006, 7, 8, the way to make these devices was take a beautiful ion beam sputtered multi-layer film, usually on a silicon wafer, and do a patterning process, lithographic definition, and then etching, and make, say, cantilevers or bridges or other devices out of this, and then, probe the mechanical resonance of those devices. And of course, you could get really high reflectivity, as I said. This is the gold standard of optical coatings, but the mechanical cues were quite limited, a few thousand. And this is one of those instances if you go back in the literature and look at what LIGO had measured, that is what you would expect. Like they had already shown that these materials had relatively high elastic loss, which limited the mechanical quality factor of those devices. So then, like Markus said, I sent this random rude email, like, what are you guys doing? No. I sent an email just saying, like, hey, this is super interesting. I had come across this paper. I was already making micromechanical devices out of single crystal semiconductors, and it seemed as though the inherent quality factor, mechanical quality factor of those were higher. And so I was like, I think we can get comparable reflectivity with work, but we would have intrinsically higher mechanical Q with these devices. And so that was the premise here. But what's nice in this case is this is still on its original growth substrate. So you do the epitaxial growth, you do the same lithography and etching, you make these structures, and with some work I can get reflectivity that's comparable, but then right away you see the mechanical Q is much higher, factor of 10 or 100 depending on the operating conditions. And so that's where this all started. Like, well, let's swap from these amorphous coatings to these single crystalline coatings, and we can get some nice improvements in the optomechanical resonators. And then as Markus already introduced, what's perfect is the introduction was like the intro to my talk. So So unbeknownst to us, this had much wider ranging impact than just the cavity optomechanics space. And it's something that we weren't aware of at the time. And so it turns out this is really a scale independent problem. If you have excess elastic loss in your materials, this drives inherent thermomechanical fluctuations in, say, an interferometer if you make a resonant cavity. And that becomes an issue in these cavity stabilized laser systems, which I'll go into more detail in a minute, all the way up through these huge interferometers, right, the gravitational-wave detectors, which is a 4-kilometer baseline detector with 2 mirrors here and a beam splitter, and then a mirror down there and a mirror way down there. And it's amazing to think about the fact that you are limited in performance in that 4-kilometer long detector by these 10 micron-ish thick coatings, right, on the test masses at the end of that long vacuum tunnel. And it is really the inherent thermomechanical fluctuations that are the problem. But I'll make more sense of that here. So I just want to give a nice conceptual picture of how that works. So I had that reference cavity, which is a simple FabriPro cavity shown in the previous slide. And here's a cartoon I made of it. So you have 2 mirrors connected to a rigid spacer. And the mirrors consist of that high reflectivity coating, which is deposited on your carrier substrate. And the light is resonating in vacuum. So you have a vacuum bore drilled through that cavity, which is important to keep in mind. And in a perfect world, you want this reference cavity to be as stable as possible. This is a simple FabriPro system. You're going to lock an external laser to it, and you're going to use this to drive down the noise of your laser. I'll show that in more detail in a minute. But this thing sits at a finite temperature, right? It's a mechanical system with a lot of degrees of freedom, and the thermal bath is pumping all the mechanical modes of that device. It could be a flexural mode of that cylinder. It could be some breathing mode of the cylinder, or it could be surface acoustic modes on the coatings and so on. But you have this forest of mechanical modes that are active in this system, right? And so what I want to show here is how the elastic loss impacts the magnitude of that noise. So I'm going to bring up a plot, which is the noise power spectral density of that system, basically the amplitude of motion for a select mechanical mode of that device as a function of frequency. Note there's 3 curves. I'll explain that in a second. But here we're going to be averaging, right? So we're going to lock an external laser to this, and we are going to be looking at ranges of frequency that are far below the internal mechanical resonances of that system, right? So we're looking at the off-resonant tail of that device. And as I mentioned, I showed 3 curves, and what I'm doing here is I'm changing the quality factor, I'm changing the elastic loss of that mode, but everything else is staying the same. Its stiffness, its effective mass, and so on. And as I reduce the elastic loss, I start to pick up more motion on resonance, but I suppress the off-resonant motion in that system. And if I go to an extreme non-physical case where there's no elastic loss, I'd have a delta function on resonance, and I'd have no off-resonant noise. So I'm basically spectrally shaping the response by changing the elastic loss in the system. So if I have a high Q system, I have a lot more motion on resonance, but I have a quieter region off resonance, which is where we care about here. So that's the whole premise. So if I choose the right materials to reduce the elastic loss of the coating of the substrate and the spacer, I win, right? I get a better result in my system here. And to quantify the spacers, here you're constrained a bit because you want a material with close to 0 thermal expansion, but you can choose materials like ultra-low expansion glass or ULE, which has a mechanical quality factor of a few 100,000. And melt-grown fused silica, which is the typical substrate material, has mechanical quality factors in the millions, tens of millions range, which is a huge mechanical quality factor. And keep in mind what I showed on the slides previously, when ion beam sputtered coating, you had a Q of like 2,000. So you can see a huge discrepancy in the mechanical Q of the coating versus the other materials. The other problem is the first thing the optical field sees is the coating, right? So you have a strong interaction, you have a poor elastic loss. And so by swapping to the crystalline coatings and reducing that elastic loss, you can make a big impact on the performance of the system. This was some really nice work by Peter Salson, came out in 1990, and it just showed basically how this worked. Look, LIGO is likely going to be limited by this elastic loss issue. For those with an electrical engineering background, this is the same as Johnson noise in a resistor, but in the mechanical domain. So you have like a mechanical loss process that drives just inherent noise in the system. It depends, of course, on the temperature, KT, and then what we talked about here, phi, the elastic loss of that system. I will point out, because I show this slide a lot, and then I get people that we don't use this anymore. We don't do this whole like infinite series of all the mechanical resonances. So now it's just done numerically. So you put it into COMSOL, and you look at like what's my optical field C first, and it's pushing on the coatings, and I can see how much strain energy is in the coatings, and I can plug in the elastic loss and so on. But it's much nicer to me to see conceptually how it works in the that nice like modal expansion method. I think it's a clear picture to me, and I like nice conceptual pictures. Of course, COMSOL works. Like plug it in and you get the right result. So that's now I'll step way back, right? Optical coatings have a tremendously long history. You have the first arc evaporated coatings in the mid-19th century, right, which were just a nuisance in arc lamps. But then people figured out, look, I'm generating a thin film coating. That's kind of neat. Like, what can I do with that? So then you had improvements in vacuum technology and deposition techniques with e-beam evaporation and then magnetron sputtering and so on. And so you slowly like improve the technology. Then you have the development of ion beam sputtered coatings, which are amazing. But then you have issues like this Brownian noise I just talked about, right? This inherent thermomechanical motion, which may be a limitation in some of these very cutting edge metrology applications like LIGO or laser systems for optical atomic clocks. And so the way to get around that was, well, let's develop these single crystal mirrors. But of course, there's challenges, like I talked about. You can't do direct growth anymore. Like stemming from this coding workshop that Markus and I went to in 2008 at Caltech that he mentioned, I got an email like, I'm going to send you a piece of glass, and you do molecular beam epitaxy and put your beautiful coating on the surface. And I'm like, that's not how that works. Like, I can't do single crystal growth on a amorphous base wafer. And so here's where now you have to put a little bit of extra effort into making these coatings. And so the basic idea is now you can't do direct deposition anymore. So I have to separately grow that single crystal structure on its initial seed, single crystal wafer. And then I have to use a transfer process to combine them together. This is generally now, there's this whole field of compound semiconductor on insulator materials, which is used for photonic integrated circuits or planar light wave circuits. And then for us, for making these large discrete optics. But there was a nice cover article from Optics Photonics News that covered that in detail. So basic premise is we're going to use standard epitaxial growth techniques to grow this single crystal multilayer on a lattice-matched base wafer. So all that, again, starts out normal. This is the same work from 1975 from Bell Labs. So, design your coating for whatever center wavelength, whatever reflectivity, whatever the design of that could be, multi-band or whatever. Now you're going to use a lithographic etch process to define the coating area, whatever that might be. You can do whatever in-plane shape you want, whatever size you want. And then you're going to selectively etch out, in this exact example, a small coating disk from that larger wafer. And you're going to take this and directly bond it onto the carrier substrate. And again, it was in the title, it was Vienna-born technology. So I used to work at ZMNS, which at the time was on Florigasa by the TU. And I would go in there and I'd fiddle around with etching out these little disks of material and trying to bond them onto the carrier substrates. And this is a direct bonding process. So there's no glue, there's no solder, no adhesive, because I do not want additional lossy materials in that stack, right? I just went through all this work. I need the highest mechanical quality factor possible. And the challenge here was there are direct bonding processes that have been demonstrated, but bonding to a curved surface had not been done before. So it's like I need to make a compliant system, bond it with no defects, no trapped particles, and so on. And yeah, those were made, on Florigasa, which was really fun. Some days of frustration, like this is the dumbest story, but I'm going to tell it. So I was making early optics. I got some nice prototypes. They looked great. And then we got some better epitaxial material, and I wanted to make another round. And all of a sudden, nothing was working. I could not get clean bonds. I was trying as hard as I could. I did one bond and the coating cracked, and I stormed out of the clean room, took off my bunny suit, went into the bathroom, and slammed the stall door just as hard as I could. I was so furious. And the light fixture fell off the ceiling and hit me in the head and reminded me to just calm down. It was like the universe telling me it's not that big of a deal. Like, it had to smack me on the head with a light fixture. I had to tell a maintenance person that I'd knocked the light down and then, go back in the clean room and just try again. So, it took a long time. It was a lot of work, but once you got the process working, it was clear. You just have to be very careful that you don't have dirt, debris, contamination, and so on at that interface. So, in the end, now it's amazing to look back because those initial optics were made between 2010 and 2011. And now, we do coatings on a wide variety of substrates, fused silica, silicon carbide, silicon, sapphire, YAG, vanidates, so on. Can do parts up to 20 centimeters in diameter, I'll show in more detail, to very tight radii of curvature, so down to 5 centimeters, which is pretty significant curvature. And in a parallel path, worked very hard to pull the optical losses down as much as possible, to reduce the scatter, reduce the absorption, control the transmission, and so on. And we can make exceedingly high finesse mirror. We've delivered parts with finesse in excess of 700,000, which is reflectance greater than 99.9995%, which is quite incredible. And then the additional selling points beyond just this flexibility in substrate material and low optical losses are, of course, you can do very low Brownian noise due to the low excess elastic loss in the system. You can do record levels of mid-infrared optical performance, which I'll point out today. And then there's high thermal conductivity in the system compared to the glassy oxides. And everything we make is based on direct bonding. And I will correct, when I say we, right, this was formerly Crystalline Mirror Solutions, which was the spin-out company from the university, and then Thorlabs Crystalline Solutions. And now, hopefully, again in Arizona, which will take some new paths. So I'm going to focus on the elastic loss issue. And you've now seen all the details conceptually how this works. And the aim here is just to improve the world's best timekeeping instruments and the world's best spatial measurement systems, which are the gravitational-wave detectors. I'll dive a bit deeper into the clock systems. I am not a clock person, but I can give you basic overview of how this works. So you want to make an optical clock work. The core of this is going to be your trapped neutral atom lattice or trapped single ions, and that is your absolute frequency reference, right? You're going to drive some desired electronic resonance in that atom, electronic transition, but you need to drive it with a laser, an optical local oscillator that has comparable line width, right? If you have a big, wide line width laser, that's just going to be convolved in that measurement of that transition, and you're not going to really gain anything. And these atomic line widths have line widths on the order of a millihertz, which means you need a millihertz laser, which is incredible to think about it, laser with a millihertz line width. And then ultimately, you drive that transition with your oscillator, but this is at hundreds of terahertz. And now you need to divide that frequency down to a measurable range and typically use a frequency comb to do that, count those oscillations, and then there's your clock, right? Grossly simplified. But the main point here is that typical semiconductor lasers have terrible, megahertz line widths. That's not going to work at all if you're targeting millihertz transitions. And so you got a grating or resonator stabilize that, and that'll get you to sub-kilohertz, but you're still way off. And now to drop by orders of magnitude more, you need to cavity stabilize that system. And so now let's go on to cavity stabilization. So that's what we're building here. We're building these ultra-stable reference cavities to produce these very long coherence length or time laser systems. So you take your already decent sort of kilohertz or sub-kilohertz laser, you tap some light off of it, and you put that light incident on that ultra-stable resonator. And every time that laser tries to walk off that resonance from some environmental perturbations or something else, you have a servo system that corrects it and parks it back on the resonance of that optical cavity. So you are imprinting the stability of that cavity onto the output of the laser there. So you need as stable as a resonator as possible. And so just to quantify that, because it's always amazing to me, ultimately the frequency stability depends on the length stability of the cavity, any index changes in the volume, and then any noise imprinted by the locking loop. And it's amazing what human beings can do when they put their mind to it, but you can remove this index perturbations, you can remove the noise from the locking loop, and you're ultimately limited by the length stability of that cavity. And we're not talking about macro length stability. We're talking about Brownian motion of that optical cavity. And so, especially early on when I give these talks, people just could not wrap their head around. You're used to like trapped atoms or pollen grains in a liquid when you think of Brownian motion, not bulk objects, right? But to quantify it, the state-of-the-art optical laser systems have frequency instabilities now in the 10 to the minus 17 range, but let's even go to 10 to the minus 16. If that cavity is 10 centimeters long, you got to suppress length fluctuations below 10 to the minus 17 meters, which is deeply sub-proton sized, right? So these are tiny fluctuations that you're going to see in that system. So again, just really fascinating, like how hard people work, right, to make these ultra-stable lasers. And we made a whole zoo of these things over the years. So the most advanced are these cryogenic silicon resonators. I'll talk about that in more detail in a minute. But these really fun transportable cavities, that was part of a DARPA project to make a transportable clock system. And then these larger lab grade systems. And I'll briefly touch on this space qualified system. And then of course, like I said, on the commercial side, we'd make these standard reference cavities that could be sold as is or installed in a vacuum chamber. And you have to, stable temperature, low or high vacuum, and a good PDH lock, right, to maintain lock to that cavity, and then you can make your turnkey fantastic laser system. I'll highlight some nice stuff here. This was the highest finesse cavity that we ever sold commercially, so this had more than 700,000 finesse at 1550, which was quite exciting. This was for a really cool microwave generation system at Femto ST, and I'm going to butcher this, Besançon, France. My French is terrible. And then we also worked closely with Menlo Systems, and they would build these full turnkey cavity stabilized lasers. I make this joke all the time. I consider that a transportable system because it has wheels. Yeah, I wouldn't take it anywhere, but you can at least move it in your lab slightly and then lock it down. But the neat thing was if you put, so that vacuum chamber I keep showing sits at the bottom here on an active isolation platform. And if you compare the performance of ion beam sputtered coated versions of that cavity with the crystalline coated versions, you can see a clear reduction in noise. Again, it's just amazing that in this rack-mounted turnkey system, you can see the reduction in Brownian noise having an impact on the performance of the laser. And even in our lab in Santa Barbara, we had built up 2 of our own cavity-stabilized lasers. It's basically 2 deconstructed versions of that ORS. Again, that same vacuum chamber sitting here and here, and these acoustic chambers on active isolation platforms. 2 Thorlabs ULN lasers, 2 Menlo Synchro lock, like PDH lock boxes, and we can do fun experiments. It's much easier to measure noise in a short cavity because as the mirrors get closer together, it's a larger fractional change in length than when the mirrors are far apart. So this is like anti-LIGO, it's super short. But even in our lab in Santa Barbara, we could measure directly like a version of that cavity with ion beam sputter mirrors versus a version of that cavity with the crystalline coatings. What becomes challenging is this is clearly limited by the coating Brownian noise, but as you go down to the crystalline coatings with their lower noise, if you look at to quantify that now, it's only a third of the noise now. So you're also seeing like thermoelastic effects in the substrate, which I won't go into, and other coating thermo-optic effects and so on. So you're basically pushing those noise floors down, but there's always another layer of noise somewhere, right, that you're going to run into. But again, the joke I always made here is this was the lowest noise laser in Santa Barbara by far. So not a lot of competition locally. And then there's another fun research effort, which were these space-qualified cavities. So this was a fun project with led by Airbus, ESA funded. We worked with ADS, NPL, a bunch of folks. And so we just did the cavity assembly, so made the mirrors, assembled the cavity, and it went through high acceleration tests up at 360 Gs of shock and proton exposure and gamma ray exposure and temperature excursions and all kinds of stuff. And it was really neat. Passed all these tests and made it to a high technology readiness level, or TRL. And maybe one day soon, there'll be a satellite platform with one of these cavities on it. So that was fun. And then these are the most state-of-the-art systems. So as I showed on that large equation earlier, KT matters here. So if you lower the temperature, you also inherently lower the Brownian noise. And so the most advanced systems are either cryogenic sapphire or cryogenic silicon. And the cryogenic silicon effort started here when I was still in Vienna, 2013, which is amazing. So we got DARPA funding that came over here. And we had a concurrent effort called Kesakas, there, with some folks at PTB in Braunschweig. And it is incredible to think back. It took 12 years to actually get these to their noise floor. June Yi, who's the PI that Oliver knows well, Markus knows well, he likes to do it in hertz per root, or hertz per root hertz, is that right? Or no, hertz per hertz squared per hertz. The numbers look even more impressive when it's 10 to the minus 34, which is just ridiculous. But more reasonable units here. These things are now at the point where the instability is 10 to the minus 17, which is just incredible. So this laser has a line width on the order of like single-digit millihertz, 2, 3 millihertz, something insane. And the coherence time of that laser is 30 seconds, which you can go 24 times to the moon, right, in 30 seconds, which is amazing. And theoretically, with some of the other noise removed, this thing would drop down to, you'd get minutes of coherence time. But yeah, there's the noise floor with the ion beam sputtered coatings, and again, from that reduction in elastic loss, you can push the noise floor down on these. So really incredible work. Now the opposite scale, can we make large area mirrors for LIGO? And here, technically, everything looks good in terms of optical performance and mechanical performance. It is an engineering challenge, though, to scale up to large size, right? This is a single device where you can't have debris or particles or imperfection, so the crystal growth needs to be perfect and the transfer needs to be perfect. And that is the scale we're looking at. It's a 35, 34 centimeter diameter mirror. There's a human for scale. And this is extremely challenging optics. And so just to walk through the potential improvements in performance, though, that's the current sensitivity in terms of strain of the LIGO Livingston Observatory. And I know it's a busy plot, but just focus on the red curve there. Right now, that's up here. So that limits the performance. But if you were to swap to crystalline coatings, you would drop the Brownian noise floor down to there. So that's my MS Paint crystalline coat. But you can see it's a significant, like 5-fold improvement in strain sensitivity in that system, which means you open up, it's like the cube of the sensitivity improvement in terms of the volume of space you can probe. But again, the challenge is their beam size is 11 centimeters, right? So I need to make huge coatings. And so we're currently at 20 centimeters, but we need to get to 30 centimeters to be viable for LIGO. And we've come a long way. So 10 years ago, we were making the first 50 millimeter diameter coatings, then 100 millimeter diameter coatings, 2018 or so, and then up to 200 millimeter diameter more recently. And the neat thing is, in principle, all the infrastructure is there. So semiconductor production technology runs at huge wafer scale. You can do 18-inch, 45 centimeter silicon, right? So we can leverage all of this technology. And so at Thorlabs Crystalline Solutions, we had built up really nice inspection capabilities. We had a commercial wafer bonder. And then this, for anyone that does microfab work, that's 11 liters of etch solution, which is ridiculous. And that's a big vat of FLUSOIR, hydrofluoric acid, everyone's favorite chemical. So, but we could produce these very high performance optics up to 20 centimeters in diameter. And these are on thin substrates just for demonstration purposes. And we have seed money now to start making 30 centimeter diameter parts. Now I'm going to totally switch gears. So you learned all about low Brownian noise and pushing the optical performance of these things. And now I'm going to move on to the mid-infrared optics. So here what matters is optical performance. So we're going to build an enhancement cavity, and we're going to measure weak absorbers intracavity. And ideally, the mirrors have no absorption themselves. So then you just inherently see the loss like intracavity there. And this is really nice for a variety of applications in atmospheric chemistry, environmental monitoring, and so on. But the thing to keep in mind is that most of the coating technologies out at these long wavelengths are far inferior compared to ion beam sputtering. And so you have really significant losses, maybe in the tens of ppm, potentially in the hundreds of parts per million level. Right? So if you want to go to high finesse, you need to look at alternative solutions. And so we initially were focusing on the wavelength range from 3 to 5 microns, and you can do nice measurements on CO2 and CO and nitrous oxide and water and so on. Again, you'll see some examples of this. And what looks promising is in the gallium arsenide-based system, if you look at absorption as a function of, this is a interpolated plot from a bunch of different mirror designs interpolated together. So you're taking into account the penetration depth and the absorption and so on. If you can minimize the background impurity level in your gas AlGaAs coating, you can push to less than 10 parts per million of absorption out to about 6.5 microns. And keep in mind, the state-of-the-art out there is like many tens of parts per million. So like, you know, way above this plot. And another one, 10.6 microns is a good mile marker. The record currently is 2,000 parts per million of absorption. But you know, I'm shooting for 50 parts per million. So it's significant reduction in loss, just because of this high structural perfection, low impurity level of this molecular beam epitaxy growth process. And so we have a lot of data down here in the NIR IR. I just put a big block. You know, we're getting 1 to less than 1 ppm of absorption. And then we've been slowly filling in kind of mile markers as we move out to longer wavelengths. There's another one coming soon out here. And this is, again, a fairly long-standing connection. So Oliver was a postdoc, so Professor Heckel, be formal there, at Juni's group in Boulder. And they were looking for low-loss mirrors for this atmospheric chemistry experiment they were running, looking for this intermediate compound, transdoco, or the deuterated version of transhoco. Center wavelength, 3.7 microns, yeah. And the challenge was most of the mirrors they would purchase commercially had hundreds of ppm of absorption. So could we make low-loss mirrors for this experiment? We got some seedling money from DARPA, quickly turned around some prototypes, and this allowed them to make some really nice, you know, frequency comb based spectroscopy measurements to identify this compound. Our mirrors, though, still had comparable loss. Like they'd had state-of-the-art levels of performance, but not exceptional levels of performance. So there were some drawbacks in these devices. The other issue was this is, again, an atmospheric chemistry experiment. This is not a mirror metrology experiment. You're not using this to characterize the mirrors. So again, the mirrors needed improvement. We already had a very nice result with an immediate science paper, but there was room for improvement in the mirrors, and there was room to dive deeper into the loss processes in these things. So for really nice collaboration, you know, locally here, doing metrology, and then us at Thorlabs Crystalline Solutions producing the mirrors, we pushed forward. One challenge is, you know, that Bragg mirror requires a lot of layers. So this is on the order of 80, 90 something total layers. And as you go to longer wavelengths, that quarter wave condition gets thicker and thicker. So these are extremely thick coatings. And this really starts to push the limits of crystal growth in these materials. And so that was one of the reasons we had sort of insufficient material quality in the first example. So we thought, well, we're good at bonding. Let's just keep bonding. So we'll grow half the mirror, bond the two half mirrors to each other, and then bond that to a carrier substrate. Okay, now we could cap the crystal growth thickness, maintain low defect density, and make this thing with added complexity in manufacturing. For this first example, we weren't sure what level of losses we would have. I'm just going to fill this in. So we put the transmission very high, like more than 100 parts per million. The fear was that the absorption and scatter would be so high that if we had low transmission, the cavity at some point will become a black hole. Right? If you imagine that the per mirror loss is so high, no light will come out of this cavity. It gets difficult to measure. So we shot for a relatively high transmission. But the very fun outcome here, and this was driven by Georg Winkler, was we saw absorption and scatter at the less than 10 part per million level, which is extremely exciting. And this matched our theory in that plot I showed earlier. And now the easy step was, well, let's just further reduce the transmission in the system. So add a few more layer pairs, make these mirrors. And this is where the results started to get very exciting. So we're able to push to a finesse in excess of 200,000, which means a reflectivity, approaching 5 nines, 99.999%, which is a completely new sort of paradigm for mid-infrared optics. So that was very exciting. But again, we're still doing this multiple step bonding process. The uniformity wasn't great in these mirrors and so on. And then there was a fantastic contribution again from Oliver, the group here. Is there another way to make these where we're not doing the full mirror crystal growth or the full all epitaxial structure? And so that was the development of these so-called hybrid mirrors. And now we pulled in another partner from University of Neuchâtel, so a colleague, Valentin Wittwer, that Oliver had worked with. And I'll bring back that old plot. Keep in mind that the field strength drops off rapidly in these mirrors. And so I can tolerate much higher optical loss at the base of the structure and then put the low loss sort of cap on top of these. And the nice thing now is I can use a traditional sputtering process to make the base of the mirror. And these would normally be not ideal materials to work at this wavelength range. But because, again, the field strength is so low down there, I can just work with this thin epitaxial structure on the surface. And so, yeah, filling in all the details, we made these all crystalline structures. Now we started producing these hybrid structures. And initial metrology was always run in Vienna to feed back on what were the total losses in these mirrors, which was a really fantastic partnership. And then, we made with Neuchâtel the base coatings, then bonded the crystalline coatings onto it, and did sort of a round-robin series of measurements in Vienna. We set up metrology in Santa Barbara, and then with outside collaborators in NIST. And here's some pictures of some of those early devices. You can see the sputtered film, sort of interference effects, kind of rainbow colors with the crystalline coating discs on the surface. And now we have these really pretty larger diameter, larger aperture mirrors, and we've pushed the finesse to absurd levels, over 400,000 in the mid-IR. And so that means scatter plus absorption is below 3 parts per million. And again, for fun numbers, these systems are now installed in a large spectrometer, about 75 centimeters long, built by some collaborators at NIST Gaithersburg. This guy, AJ Fleischer, working with Joe Hodges there. And the effective path length of that cavity, because of the high reflectivity of the mirrors, is more than 100 kilometers, something like 120 kilometers because of all the bounces. And so you can do extremely precise measurements of trace gases like part per billion level carbon monoxide or part per trillion level nitrous oxide detection, and ultra pure nitrogen gas that you would use for semiconductor processes and so on. And it's just really neat. So owing to the very low loss of the mirrors, you can now build these fantastic spectrometers. And so the fun thing is producing now 3.3 micron mirrors for methane-ethane detection, 3 micron mirrors for I don't know what else at NIST and so on. But we can now fill in anything out to 5 microns, and then there's a path to go even to 10 microns beyond and like push down and fill in all these wavelengths. And really enabled by this hybrid mirror approach, because now we don't have to grow these extremely thick epi structures. We can do a thin cap and put like a decent performing multi-layer below. And I'm going to go just one final slide here, which just sort of quad chart style of like all the fun stuff you can do based on direct bonding. So over the years, people would pop up and say, again, like, hey, you guys bond stuff all the time. Can you bond this for me? So one was these optically pumped thin disk lasers. This is a semiconductor active region sandwiched between 2 single crystal silicon carbide plates. It's all for thermal management. Again, I don't have time to go through the full details, but the basic idea is you have 2 single crystal silicon carbide chips on each side to just get the heat out of these structures. And we've made 30-watt emitters in the NIR IR based on this heavy bonding process. To make these, and the aim is to make a sodium laser guide star of 589 nanometers. It was a really fun, successful project. Also have done fun like electro-optic materials bonded to photonic integrated circuits like lithium niobate, lithium tantalate, barium titanate. on passive photonic integrated circuits. And the fun one was lithium niobate. We got all the way up to 4-inch wafer production, which was pretty cool. This is a fun paper that just came out. We put indium phosphide on C-plane sapphire to make a modulator for the free electron laser at UCSB. So it's an optically driven switch, effectively. Like, this is transparent to microwaves with no illumination, but then if you hit the indium phosphide with an above bandgap laser, that becomes reflective, and so you can chop the laser light coming out of the free electron laser. And what was crazy is this thing can take kilowatts of microwave power, which was quite impressive. And so it was an easy way to make a basically a modulator for the free electron laser at UCSB. So it was a fun little side project. And then I think one of the more exciting directions is you can make these fantastic nonlinear circuits for entangled photon generation, for squeeze light generation. You can leverage the Chi2 and Chi3 processes in these compound semiconductor materials like aluminum gallium arsenide, indium gallium phosphide, by cladding them with low index oxides. So you have high intensity in these waveguide structures. So we'll transfer thin films of the compound semiconductors at wafer scale onto these oxidized silicon wafers, and then someone will make a PLC out of that. This primary collaborators there have been Galen Moody and John Bowers at UCSB. And then we can leverage that now to make even larger structures up to 8-inch. So there's another commercial company called Illuma in Santa Barbara that we can supply these bonded structures to make, again, large-scale photonic integrated circuits up to 8-inch. So yeah, that's pretty much it. I covered a lot of ground from low Brownian noise and low loss mid-infrared mirrors, and then all the fun like little side quests that came up. But the basic message is, I think this is a really unique space to work in, this combination of semiconductor materials and microfab techniques with bulk optics, just to enable a lot of very fun sort of scientific advancements, and high optical quality in these compound semiconductors now, very low elastic loss, making the world's lowest noise laser systems. And yeah, so I'm excited to get started at Arizona. Obviously now it'll be more on a researchy path, so continue making large area optics for LIGO, push into some of these alternative wavelength ranges, like very short wavelengths or very long wavelengths. And then get back to my cavity optomechanics roots. So do some fun microfabricated devices there. And then pushing on these high-powered disk laser structures. I think there's a lot of utility in these bonded-based structures because they are thermally optimized. Put it on diamond or silicon carbide heat spreaders. With direct bonding, dump a lot of heat out of these. So yeah, thank all the collaborators over the year. We had this fantastic ERC proof of concept project that really kicked stuff off here. Some nice funding from DARPA and so on. Yeah, looking forward to getting started at Arizona, and thank you again for your attention.
Garrett, thank you so much. Floor is open for questions, and I need to throw the microphone because Bile has still not bought the cubes to throw.
I'll start. Thanks, Garrett. Thanks for the visibility too. You mentioned the spaceborne cavities.
Yeah.
So of course I get curious, how radiation hard is the structure? Because that should be a nightmare, right? I mean, any defect kind of is a problem.
So far it looks, so I'll give you the pros. So what we've seen so far is no degradation from proton or gamma ray exposure. And the simple experiments were just measure finesse before and after. And there was no change. The other good news is that most space-based photovoltaics, like power converters for satellites, already use gallium arsenide-based materials. So it's a known radiation-hard material. The question, like you're asking, what happens at the bond interface? We don't know. We didn't see any changes. We didn't see any issues. Whatever experiments were done, again, by this ESA collaboration. But it's still an open question. Are there long-term issues? But they push these things to a normal lifespan of a satellite, and it was fine. So as far as I know, it's okay. And the glasses are more the problem. They yellow and get damaged themselves. So I think the coating will be fine. The bonded interface at least holds up through the normal lifetime of a satellite, but remains to be seen what else could happen. Yeah, exactly. Single crystal silicon, cryogenic,
So here's the obvious question: how long for LIGO to pick up on the crystalline mirrors?
I'll tell you I showed all the positives. The negatives are there's clearly efforts to get high uniformity, low optical loss systems. The challenge we have is they already have an existing ion beam sputtered approach, which works. So if you can find different formulations of sputtered films, you can instantly turn that on. It's really a financially difficult proposition because today I can go buy 20 centimeter diameter gallium arsenide. But if I go to buy 30 centimeter diameter gallium arsenide, it is on the order of $10 million to buy a custom boule that's cut and so on. And that's step 0, right? And then I have to do epitaxial growth and transfer and so on. So it gets into the $20 million plus effort to try, and there's still risk. So the effort is just to keep marching and de-risk everything, right? Like how low of cost can we do for wafer production, for epitaxy and so on. So I think it's still, if I'm going to be, I'm optimistic because the amorphous coatings have shown very limited improvement. Tens of % level, which is great, but that's over 20 years, right? And we're looking at instantaneous, many-fold improvements, right? So it just depends on if NSF or someone's going to open up that budget and pay for it. But we need to make the risk extremely low. So, yeah. I think within a few years, we're making prototypes at 30 centimeters, I'll say that.
Yeah. Thanks, Garrett. That's really amazing to see what happened.
Yeah, good to see you, Nicola.
So my question is a bit off topic because it's not coating, but maybe you can still tell me the super high finesse cavity, the 700,000 one you showed. It has this triangular shape. Why is that?
So all of these cavities, you're trying to minimize acceleration sensitivity also. So I'll try to describe it quickly. Like imagine you had a cylindrical spacer. Again, it has these like bending modes and other mechanical modes. So if you hold it rigidly and tightly at an arbitrary spot, vibrations from the environment will come in and shake that cavity. But even on that cylinder, you can do smart things. Like if you look at that cylinder bending between concave and convex, you can see there's 2 points that don't move. And so if you hold it there, you reduce the acceleration coupling into it. You reduce the vibration coupling into it by holding at these sort of like nodal positions in the motion. And so all the cavities had funky shapes. I won't go back, but you saw some had ribs and ridges. You saw that triangular one. You saw the cubic one with these cutouts. And you hold it at these points of symmetry such that there's no mechanical motion there, because that then reduces the acoustic coupling or seismic coupling to the environment. And that weird triangular shape was, I'm just going to say it, like it was a French group and they had very interesting designs. So it was like extremely complex way to minimize acceleration sensitivity to make this prismatic design that was held at these specific points that had minimal acoustic coupling. Yeah. So but it's neat. It's a whole field of its own. Like people do all this mechanical design to decouple from the environment. So yeah, it's pretty neat. Ideally, you would have a levitated cavity, right? Because you would want this thing free floating with no connections to the environment, because then you don't couple vibration in.
Yeah, you mentioned the cryogenic systems. What makes them such a challenge? Like, is it the thermal expansion of the materials, or what's difficult?
Vibration. So the thermal expansion is actually really interesting. So if you saw, I was showing silicon versions. I'm going to go to a less obvious one. Sapphire, all materials as you cool towards 0 Kelvin, the thermal expansion tends to 0, right? But some materials do weird things, like silicon and gallium arsenide, because this cubic symmetry, they actually go to a negative thermal expansion and then return to positive thermal expansion. But because of this cross through, there's 2 temperatures at which you have 0 thermal expansion. So if you cool to those temperatures, there's no thermal expansion. So you have really nice, stable cavity at that point that you hold those temperatures. But the refrigeration system requires cycling the cryogen, and that shakes things, right? And so the hard aspect of this is trying to minimize those vibrations, but still cool the system. So I'll give an extreme example. Like, look this up if you're not familiar, but there's a Japanese gravitational wave detector called KAGRA, which uses cryogenic sapphire test masses, 2 or 3 kilometer long system, and they cool the test mass through single crystal sapphire fibers, right, that are like hundreds of microns in diameter. And it takes a month to cool the test mass, right? Because you have to so strongly decouple it from the environment to reduce vibration and so on. But that's your only thermal path in. So that's how you cool. So that's the trade-off is always this. Like, you can't rigidly hold stuff and make a large thermal contact. You have to, isolate it. But then you still have to cool it somehow. And so it's always radiation-based cooling, usually not a direct connection like that. And then the pumps circulating the cryogen cause vibration. So you have to work very hard to make low vibration cryostats. And there's good stuff out there from, again, Montana and whoever that can do this. But you have to work very hard to minimize that.
Okay, so quite simple question. How do you even bond these 20 centimeter things? How do you handle it with your hands and put it somewhere?
That's the nice thing. Like, it's hard to see in the picture, but you can buy commercial tools for that. So I think this isn't too far back. We bought from an Austrian company, EVG, Electronic Visions Group, that commercial wafer bonder. So in semiconductor world, there's a material platform called SOI, semiconductor on insulator, or silicon on insulator. And those are all made by bonding. They take an oxide layer and they bond a single crystal material onto the surface. And so there are large production machines that do that. But it is still very arts and craftsy. So we take the input wafers, we load them into this microscope, scan for defects, make sure it meets all of our defect specs. We then clean it. It is a manual cleaning process. Like, it's sitting on a spinner, you're spraying solvents, you're swabbing it. I mean, it's like the most professional dishwashing process of all time, right? Until you get to 0 particles. And then you verify that. And you hope everything stays clean, and you load it into the bonder, and then it is pressed together in the bonder. And so the 2 halves are put in, like the base substrate and then the top wafer. And then you close that and pump it out. So it's in vacuum. And then it's all controlled contact. So I'll make this quick. But imagine you took 2 flat plates and tried to slap it together. Like, the best example is you're putting a screen protector on your phone. And I took my phone and just slapped the screen protector on. It's going to be terrible, right? Spots everywhere. So I have to controllably put that on. And so the way it works here is see the hole in the center of that top disc? There's a little piston that the wafer's held up here with some little mounts. And then there's the bottom substrate. And you push from the center to make contact. And then the van der Waals force starts to pull everything together, and then you pull the spacers out and you let it drop in vacuum, right? So it's initial contact, bond wave propagates out, pull. So you need to manually make it as clean as possible, load it into the machine, and then the machine does all the pump out, controlled contact, and so on. So that's the one nice thing. Yeah, you don't have to do it yourself. So I think the good analogy is you have to either roll it on from an edge or touch from the center like you're putting a screen protector on with no particles.
I imagine those machines expect flat surfaces. So where is the magic sauce there? How do you get wafer people don't need bent stuff?
Yeah, right. But that's the nice thing. Like I said, because they're always an option to do this called bow pin bonding, where you push from the center. I can take a concave base substrate, and as long as I can deform my top part to a higher radius of curvature, it's okay. Worst case, right, is I have a concave base and I just come straight down. I'm going to have a huge void in the center because I'm going to contact at the edge. So I just need to warp the top part to have a higher radius of curvature, then make contact, and then the same process happens. I let it propagate out from there. But you can do it in here. And these are slight radii of curvature. They're typically meter scale. I mean, LIGO's kilometer or 2 or whatever. So it's barely any curvature. But for most of the optics we make, they're meter scale, half a meter. But we've made stuff down to 10 centimeters. And again, you just have to have a compliant structure that you can very severely deform and then push it into contact. Yeah. It's not as scary as it seems like it would be at first. Yeah.
Excellent. So first of all, thank you, Garrett, so much for this absolutely fantastic overview.
Thank you, Mark.
And for being here. So big hand for Garrett once more.
Thank you.
Okay, good. So that also means, and I'm not looking at Mario,